We're continuing 2015 and we've got 31 through 40. First one's pretty easy. It's just ordering acidic to basic. So if we take a look, NH4 plus is actually slightly acidic. It's the conjugate acid of a weak base. That weak base would be ammonia. And actually, the Ka of NH4 plus is the same as the Kb for acetate. So this solution, no matter what molarity it's at, would be perfectly neutral, pH 7, in water. For this, Na plus does not contribute to the pH in solution. Neither does Ba2 plus. But the reason that this is more basic than this is because we have two acetates. So the effective concentration of acetate in solution is higher, so the solution will be more basic. Okay, so we're looking at molar solubility. This one we have KSP, so just to draw it out, I don't really draw it out when I'm doing these problems because you can kind of get a sense for it, but basically we have some like concentration of this, right? And then you lose x of it and you end up with m minus x. Here, just say you start with 0. You gain x here and you gain 2x here because it's 2f minus. So if you're looking for KSP, you would do x times 2x squared, so that would be x times this, which is 4x cubed. So we can say 4x cubed is equal to 6.8 times 10 to the negative 9th. Then if we solve for x, we'll get 1.2 times 10 to the negative 3rd. 33. Okay, so this is probably not something they teach in like regular chemistry or AP chemistry. The only reason I know this equation is because I went through Atkins to find it. But basically, there's this equation that lets you convert from equilibrium constants of partial pressures to equilibrium constants of concentrations. And that's Kp equals Kc RT delta N. I'm pretty sure this is right. Delta N is the change in moles of gas of reaction. So it's final minus initial. So here it's 3 minus 3. No, it's 3 minus 4 because we have 1, 3, and then we have 3 here. So that would actually be n equals, or delta n equals -1, because -1 moles of gas change. So we're finding the ratio, right? Kc over Kp. So actually, we can rearrange this equation to say Kc over Kp equals 1 over RT to the n. And hold on, I'm kind of blanking on what R is here, but I'm pretty sure it's gas R because we have Kp here, so it should be 0.08206 if we're talking about ATMs. So if we solve this equation, and then this is at, what the heck, 723 Celsius. Okay, didn't notice that. 996 K. I'm just going to put the 1.5 to be a little more accurate. Okay, I'm not going to write the units in there, that'll just mess me up. To the negative first. So if we calculate the denominator, oops, 996.15 times that to the negative first. I mean, technically, you don't have to do 1 over to the negative first, because you can just, find it, because 1 over does the same thing as the negative first power, so you can just kind of like cancel those operations out. So you'll get that this ratio is equal to 81.74 blah blah blah, and that's 81.8. Obviously it doesn't round exactly, but that's probably just because we use slightly different temperatures or gas constants. For 34, hydronium ion concentration in a solution formed by dissolving. Okay, so this is Henderson Hasselbalch equation. It's a buffer solution. So basically, you're already given that the ammonia solution is 3 molar, and what you're assuming is that adding some solid, what you're assuming is that, please stop, is that the ammonia solution doesn't gain too much volume from you adding 1 gram of that ammonium chloride. So first we can just calculate how many moles of ammonium chloride that would be. We're not really interested in the chloride part, but because the ammonium ion is in a 1-to-1 ratio with the ammonium chloride, still a useful calculation for us. And this is in 30 mils. So if we find the concentration, we get this value. And that's for NH4+. And then the Ka of NH4 would be, if you use the Kb given and then you convert it to Ka, by dividing 10 to the negative 14th by that, and then you would want to take negative log of your Ka value in order to get pKa. So you'd get 9.26, and then you'd want to look for your pH. So then we have log base over acid, in which you would put, base over acid, so 3 on top and then 0.623 down here. So log, then we add 9.26 to that. So our pH is 9.94, and then pOH, because we're looking, we're looking for a H3O+. So this will give us our concentration, and that's, syntax error. That is 1.15 times 10 to the negative 10th, which rounds to 1.2. 35, copper hydroxide has that KSP. Okay, we're given the overall K, we want to find KF. Usually they'll tell us to find the overall K given KF, but looks like they got a little creative for this one. So basically, you want to write out the definitions for each K, and then it's really easy to see like what you have to do. So for our KSP equation, this is 2.2 times 10 to the negative 20th, and then we can see that our overall equation, we have this OH minus squared, and there's NH3. This is equal to 4.0 times 10 to the negative 7th. And we're looking for the KF, which would be this. Let me think. It would be Cu2+, and then you have NH3 to the 4th. That would be our KF. And if you think about it, you can divide this second equation by this first equation in order to achieve that KF. Because the expressions would be equivalent, so you just divide their numerical values. So if we do 4 times 10 to the negative 7th divided by 2.2 times 10 to the negative 20th, we find that KF is 1.8 times 10 to the 13th, which is C. 36. Which species represent at least 10% of total selenium in solution? Okay, so here you have only, you have only this. This is your first equivalence point, this is your second equivalence point, second half, first half. At here, this and this are in equal concentration because that's our first equivalence point. But here, all of this has been neutralized and you only have this. So that's why it would be C. 37. Okay, so when you're assigning oxidation states, just go from most sure to least sure. So the one I'm most sure about is in this case, there are no metals to be seen, so there's not going to be any hydride nonsense. So hydrogen will definitely be +1. Oxygen's probably -2. So then you get +2, -2. That's already equal to 0. I need to have an overall charge of 0, so C would contribute 0. In a galvanic cell with this thing, what occurs at the cathode? Okay, so reduction happens at the cathode, oxidation happens at the anode, so automatically get rid of either oxidation choice. And if you take a look, actually chromium is being oxidized to this, so it's not being reduced. And then Ce4+ is being reduced to Ce3+. Which two half reactions, when coupled, will make a galvanic cell that produces... Oh, okay, so this one's pretty easy. You know that you must have 4 in here, because this is astoundingly larger than everything else. So get rid of A. So in order to make this a very large positive value, you need to multiply this by -1. In other words, you need to be oxidizing aluminum metal to Al3+. And in order to make the overall E cell as large as possible, you want to add the biggest reduction potential, which is this. So 3 and 4. Okay, so 1.5. You technically don't need to do the calculations for this. You can just do it conceptually, but I will. Coulombs per second, that's what amperes are. So if you multiply by 3,000 seconds, you will get 4,500 coulombs. If you divide that by this many coulombs per moles of electron, you will get 45. You will get that there were this many moles of electrons involved. And basically here you're comparing the oxidation states of the metals and the molar masses of the entire compounds, because here you would need to convert from moles of electrons into moles of the compound, and then you would need a scale based on the oxidation state, because here it's Pb2+, but here it's thallium-1+, right? So here, if the molar mass is not, if the molar mass is less than, how do I put this better? If it's more than twice the other one, then it won't deposit more metal, because it has to deal with 2 times less. So actually, I'm speaking kind of backwards. It would have to be more than twice. And here you have +2, +3. So basically, if you just weigh the effects of the molar mass of each compound and the charge of the metal, A would just end up being most efficient for you. Alright, next time, 41 through 50.